Okay, so we're going to continue on with chapter 9. We're going to find the area of regular polygons. So you know how to find the area of triangles and trapezoids and parallelograms and different things like that. But what if it's a regular polygon? Like here I've got a regular octagon, so it's got 8 sides. So we don't really have a formula for that, do we? But essentially what you can do is divide this up into triangles and then find the area of one triangle and then basically find the area of all the triangles that would make up the figure altogether. So let's kind of go over some vocabulary first. And make sure you're taking notes on this. You'll need to know the vocabulary. And as always, pause the video when you're trying to work the examples so you'll try some of these on your own. Okay, so one thing is we call the center of the regular polygon is just the point in the center there. It's actually the center of the circumscribed circle. Like if I were to draw a circle around this and have the polygon inscribed inside it, it's the center of the circle, but it's also known as the center of the polygon. Okay, so we have a center. We have segments that are called the radii. So you're familiar with radius. It's the same concept. Oh, that's pretty crooked, but it would be, imagine like if we drew in the circle, like I had mentioned, from here to a point that's on like a vertex of the polygon will also be on the circle. So you can draw in multiple radii and make triangles. This is a new one to you probably. This one goes straight down from the center to the side and it forms a right angle. Okay, and this is called the apothem. Okay, that's the apothem. Now, when you draw in consecutive radii, so like one right after another, so I could draw it in like right here, another radius. This angle that's formed by the two radii, that angle whose vertex is on the center is known as a central angle. And as we start talking about circles here as we finish up the year, we will talk about central angles. But those are kind of the parts that you need to know for a regular polygon. Oh, also, just the side of the polygon is just known as a side. Okay, so those are all the parts that we need. So if you imagine, if I drew in all 8 radii, since this is an octagon, and since it's regular, wouldn't all 8 of those radii would form 8 congruent triangles? So if I could find the area of, say, this triangle, then I could multiply it by 8, and that would be the area of the whole figure. And that's essentially what you do. So here are the steps. So to find the area of a regular polygon when limited information is given, first thing you do is you're going to draw 2 consecutive radii and find the measure of the central angle. So I've got a regular hexagon here as an example. So you would draw in 2 consecutive radii, and I usually just draw, wow, that's really bad. Let me try that again. I guess I could use the straight edge tool, but where's the fun in that? Okay, so you draw 2 consecutive radii and then find the measure of the central angle. Remember, this is the central angle. So if I were to draw in all 6 radii all the way around the circle, all those angles would add up to 360. And so since there's 6 sides, the way you find the central angle, and I'm just going to abbreviate it CA, is you take 360 and you divide it by n, where n is going to equal the number of sides. Okay, so as an example in this problem, the central angle would be 360 divided by 6. So the central angle is going to be 60 degrees. So that pink angle would be 60 degrees. Okay, step 2 is you draw in the apothem to create 2 congruent right triangles. So if I were to take from the center, and remember the apothem goes straight down to the center of the base, it bisects the base, that would create 2 congruent right triangles. Now, when you draw in the 2 radii, since the radii are congruent, this would be an isosceles triangle. So that's why when we draw in the apothem, it creates 2 congruent right triangles. It splits those. So then it says divide the central angle by 2 and label this angle. So if this whole central angle was 60 to begin with, Now, just like this part would be half of that. So this would be 30. So look at what's created. I have a 30, and since that's 90, this would have to be 60 degrees in this particular example. So it says, determine what type of triangles are formed. If they're special right triangles, like these would be, because that's a 30, 60, 90 triangle, and we can use our appropriate formulas to find the lengths of the sides that we need. If they aren't special right triangles, so if this is not 30, 60, or 45, say it's, 32, then we'll use trigonometry to find the length. Okay, so we're going to see some examples of both. And then you use the formula to find the area once the length of the side, the apse, and the number of, that's just a typo, number of sides is known. Okay, and the formula is on this next page. Okay, it's technically a theorem. There's two ways of writing this, and I prefer the second one just because it spells everything out. Okay, so the area of a regular polygon is half the product of the apothem and the perimeter. So you can see it written like this, capital A for area, 1/2 the product of the apothem, so A, times P, where P stands for the perimeter. So like if I had a little regular hexagon, real rough sketch here, if I wanted to find the perimeter, like I know there's 6 sides, and like if I told you this side was 5, what would the perimeter be? Well, you'd say 5 times 6, right? So another way of writing the perimeter is you take the number of sides times the actual side length. I should have used something besides 5. And it looks like, let's say that's 8. So the perimeter would be 8 times 6. You would multiply the number of sides times the side length. So I prefer, instead of writing the perimeter in the formula, is this formula, just because I think it's easier. I don't know why, this just always sticks in my brain better. 1/2 SAN, 1/2 SAN. 1/2 AP and 1/2 SAN are the same thing, because perimeter is the length of the side times the number of sides. Because you can use either formula. I just like I said, I like this one because everything's kept separate and you just plug it into the equation. So that's what I'm going to use. Okay, so for these first few examples, we're going to leave our answers in simplest radical form when it applies. Okay, so let's just try this one. So find the area of a regular heptagon. So stop right there. Heptagon has how many sides? 7. So n is going to equal 7. Whose sides measure, let's say, 14.5 inches. And whose apothem measures, let's say, 6.8 inches. So I've given you the apothem. I've given you the number of sides. The S was 14.5, and then the apothem would be 6.8. So on this problem, we've got everything. We've got the sides, the number of sides, and then the apothem. So you could just plug it into our formula, 1/2 SAN. Or you could multiply n and s together separately and then multiply it. But to me, that just seems like, why have to do that separate? So technically, does the order matter when you're multiplying? I'm sure you said no. So we just multiply those together, and hopefully my calculations are correct on here. That would give us an area of about 345.1 square inches. Okay, so sometimes you'll have all the information. You can just plug it into your formula. All right, let's look at number 2. So it says find the area of a regular hexagon whose apothem measures, let's say, 8 square root of 3. Let's say centimeters. Okay, so when you're trying a problem like this, you don't really have to draw the whole hexagon. If it's a hexagon, what's the number of sides? It would be 6. So we know n is 6. So we need to figure out the s because they gave us the apothem. So the only thing that we're missing is the side length. So I would suggest drawing at least the triangle that's formed by 2 radii. So we've got one radius and then the other radius. And then I'm going to go ahead and draw in the apothem. Okay, so if you go back and look at your steps on the that we wrote down at the beginning, to find the central angle, you take 360 and you divide it by the number of sides. So this is 6. So the central angle is going to be 60 degrees. So that means between the 2 consecutive radii would be 60 degrees. So the apothem is going to cut that in half. So that makes this 30, which makes this a little 30, 60, 90 triangle. Okay, the side is what we're trying to find. So that's this. The apothem is 8 square root of 3. So this orange segment is 8 square root of 3. And so now we just use because it's a special right triangle and the direction said leave answers in simplest radical form, we're going to find the missing parts. So since that's 30, 60, and that's 90, the 8 square root of 3, is that the long leg, short leg, or hypotenuse? That's the long leg because it's opposite the 60. So I could find the short leg by dividing that by the square root of 3. So that's going to be 8. So if this is 8, this would also be 8. So the length of our whole side would be 16. So we'll use our 30, 60, 90 rules to find the part that we needed. So the side is going to be 16. So then you just multiply those together. 1/2, and of course the order doesn't matter, but I just usually put them in that order. 1/2 SAN, 1/2 SAN. 1/2 times 16 times 8 times square root of 3 times 6. So when you go to put this in your calculator, since we're leaving it in simplest radical form, remember the rule for multiplying with radicals is to multiply the coefficients. So don't put the square root of 3 in your calculator. Multiply 1/2 times 16 times 8 times 6, and hopefully I've multiplied correctly, and we get 384 square root of 3 centimeters squared. So that would be the area of the whole hexagon. So we found the area of this little triangle with the 1/2 and the side and the apothem, because that's the base and the height of that little triangle. And then by multiplying it by n, that accounts for all 6 of the triangles that would be in there if we drew them all in. Okay, so let's look at 3. Okay, find the area of a square whose radius measures, and before I give you this, we know how to find the area of a square, don't we? We already have a formula for that, side squared. Well, sometimes you're given other information, like here, the radius is not part of side squared, so we still have to go through this, use our formula here. So let's say that's 10 squared of 2 meters. Okay, so the radius would be from here to the vertex. That's going to be 10 square root of 2. That's what we have. So I'm going to draw on the other radius to make our central angle. So the central angle would be, in this case, 360 divided by the number of sides. So since it's a square, that's going to be 4. So we know the number of sides is 4. We know the radius, which is not part of what we need for our formula, but we can use that to help us find the other two. Okay, so 360 divided by 4 is 90. Now, technically, you could stop right here and use the fact that, if that's 90, and this is an isosceles triangle, these both have to be 45, or you could go ahead and draw in the apothem, and because the central angle was 90, this whole angle was 90, when you split that in half, that makes this 45. And so that makes this a little 45, 45, 90 triangle. So if the hypotenuse is 10 square root of 2, they give you 45, 45, 90 rules. How do you go from hypotenuse to leg? Well, that's going to be 10, and that's going to be 10, because you would divide that by square root of 2. So if that's 10, this is 10, so what's the whole side length? 20. So I know my side is 20, my apothem is 10. Now, you can use the 1/2 SAN, so 1/2 times 20 times 10 times 4, and that would give you 400. Or, as soon as you know the side length is 20, can't you just say the area is the side squared? That's the other way of finding the area of a square. So you could just stop and say 20 squared, which is, of course, 400. And our units would be meters squared because we're finding area. So on a square, once you know that is 20, then you could stop right there. If you had wanted to, you could have, since you knew this was 90 degrees to start with, you could have used that 45, 45, 90 triangle and found the hypotenuse that way and then done side squared. Okay, let's look at the fourth one, an equilateral triangle. Now, we already know how to find the area of a triangle too, but sometimes you're not given the same information that we're used to having. Like here, they're going to give us the apothem. So let's say the apothem measures 15 centimeters. Okay, so remember the apothem goes from the center and then it's perpendicular to the base and it bisects the base. So that's what's 15. Okay, so let's draw in our radius, our radii. All right, so step 1 is to find the central angle. So 360 divided by 3 is going to be 120. And so that means these two create 120 degrees. So we divide that by 2. That makes that 60. So we have a 30, 60, 90 triangle. Okay, so again, Keep in mind, we're trying to find the side, the apothem, the number of sides. So we have 15, we have the number of sides. We're just looking for the length of the side. Okay, so if 15 is the apothem, that's opposite the 30. That's the shorter leg, so find the longer leg. If that's 15, what's the longer leg? 15 square root of 3. So if that's 15 square root of 3, what's the length of the whole side? Well, that would be 30 square root of 3, because we know the apothem would bisect the base, because this is an isosceles triangle, so when you draw an apothem, you bisect the base. All right, so now we know that's 30 square root of 3. And so now we just crunch the numbers, as I say sometimes. So 1/2 times 30 square root of 3 times 15 times 3. And of course, again, that's in any order. We would get 1/2 times 30 is 15 times 15 times 3. So that's 675 square root of 3 centimeters squared. Now, if the directions said to round, of course, you could just stick all that in a calculator, but it said to leave answers in simplest radical form, which is typically what we do when it's a 30, 60, 90, or 45, 45, 90. Okay, so again, make sure you're trying some of these, on your own, and unpause the video and watch when you need to. All right, find the area of a regular hexagon. So we know n equals 6, whose sides measure, let's say 22 inches. So we know S, so we're missing A. Well, you guys know that I'm not very good at drawing, so I'm just going to draw the triangle that we're using. Okay, so just, if you want to draw the whole hexagon around this, by all means, please do, but you don't have to. Okay, so I know the side is 22, so this would represent the side, which means if the whole thing's 22, that's 11. All right, so we need to find the central angle. You may remember from before. So we would say 360 divided by 6, that's 60. So the central angle would be 60, which means this is going to be 30. So that means my short leg's 11. So you need to find the longer leg, because that represents the apothem. So that's going to be 11 square root of 3. So then we just multiply the numbers. 1/2 times 22 times 11 square root of 3 times 6. And that's going to give us 726 square root of 3 inches squared. Sorry if you can hear snoring. My dog Cookie is laying in here snoring. And Chevy is one of the cats is in here too. So if you hear a big crash in a minute, it's probably him knocking stuff off. Okay. Now we're going to switch over and find these to the nearest tenth, and you'll see why. So it says find the area of a regular decagon. So a decagon has how many sides? 10. With an apothem of, let's say, 21 centimeters. Okay, I definitely can't draw a regular decagon, so I'm only going to draw the triangle that would be formed by 2 consecutive radii. And so I'll draw in my apothem. And so this is what's 21. All right, so, no, Chevy, get down. Okay, so if we do 360 divided by the number of sides, which in this case would be 10, that's 36. So that means this whole angle is 36. So when we drew in the apothem, that cuts that in half. So that's 18 degrees. Now, do we have special right triangle rules for 18 degrees? No. So what do? We use trigonometry, I'm sure you're saying. So we've got the apothem. We just need to find the side. So this represents the side. So what we can do of our right triangle is I can find this little part. And so once I get this, what would I then do with that number? I would double it, right, to find the whole side. So let's use trigonometry. So what's that made up word that we use? SOHCAHTOA. So from this angle, that's the opposite leg, and this would be the adjacent leg, so we're going to use tangent. Get down, cat. So the tangent of 18 degrees would equal opposite over adjacent. And so then to solve for x, you would multiply both sides by 21. So we're going to round all intermediate values to the nearest 10th place. So that means, any values that we round throughout, we're going to round to the 10th place. So if that's 6.8, what would be the length of the whole side? That would be 13.6 for the whole side because we just double that, multiply that by 2. So that's going to be 13.6. So we've got all our information, so we just multiply it out. 1/2 times S times A times N, and I came out with 1,428 centimeters squared. Okay, so if it's not a 30, 60, 90, or a 45, 45, 90, then you just use trig. Okay, let's try another one. Okay, on this one, find the area of a regular pentagon with a radius of, let's say, 18.4 inches. So again, you could draw the whole pentagon if you like, but you certainly don't have to. So I'm just going to draw in the triangle formed by the 2 radii. So we know the radius is 18.4. So both of these will be 18.4. I'm just going to label one of them. We have to find the central angle measure to figure out what kind of triangle we're working with. So if it's a pentagon, the number of sides would be 5. So we divide by 5, get 72. So then take half of 72, because remember that's the whole central angle formed by the 2 radii. So half of that's 36. So I don't have the apothem or the number of sides. Glad my camera's not on. My cat's being it. Anyway. So I'm going to find the apothem first. Okay, so from this angle, that's the adjacent leg, and then that's the hypotenuse. So we will use sine, cosine, or tangent. I'm sure you all say cosine. So the cosine of 36 degrees equals adjacent over hypotenuse. So I would multiply 18.4 times the cosine of 36, and that would round to give me 14.9. So I get 14.9 as my rounded value there. And then to find the side, I could technically use Pythagorean theorem because I know 2 of the sides now. I would probably just use trig again. I'm going to call this x. But just remember, does x represent the side? It's only half the side, right? So once you find the side, we're going to have to double it to account for the whole side. So I'm going to use the original information. So that's the opposite leg, and that's the hypotenuse. So I'm going to use the sine of 36 degrees equals opposite over hypotenuse. So to solve for x, I would multiply both sides by 18.4. So that gives me x is equal to 10.8. So if this is 10.8, then the whole side, you would have to multiply that by 2. So 10.8 doubled would give us 21.6. And then you just multiply it out. 1/2 times 21.6 times 14.9 times 5. So the area would be, I got this, 804.6 inches squared. All right, just a couple more. Number 8. So this one, find the area of a regular heptagon. So a heptagon has how many sides? 7. With the side length of, let's say, 32.4 meters. Okay, so we've got the side, we've got the number of sides, we just need the apothem. Okay, so I'm going to draw in my 2 radii and the apothem. So if the side is 32.4, we just work with the right triangle, so what would that make this? So that would be 16.2, right? Okay, so let's find the central angle. So 360 divided by 7 is, doesn't work out to be a whole number. So if we divide 360 by 7, we get to the nearest tenth place, 51.4. So that would mean that half of that angle, if we take 51.4 and divide it by 2, we would get 25.7. Okay, so we found the central angle, 360 divided by 7, and then we divided that by 2. So I need to find the apothem. So we've got the opposite leg, and then that's the adjacent leg. So what would we use? We would use tangent. So the tangent of 25.7 degrees would equal 16.2 divided by the apothem. So opposite over adjacent. So how do you find the value of A there when A is in the denominator? Remember, these two essentially have to switch places. You have to multiply both sides by A and then divide both sides by the tangent of 25.7. So the apothem, I got about 33.7. So let's multiply those numbers. So 1/2 times the side times the apothem times 7. And I have to multiply this out because I used the wrong angle on my notes. So I got 3,821.58. So since it said round to the nearest tenth, I'm going to round that to 0.6. So hopefully that is what you guys got. Again, I had worked it out incorrectly because I used the wrong angle measure. Okay, so hopefully that makes sense. There's one last problem I want to show you. Okay, when it's an equilateral triangle, if you know the side, think about that in this equilateral triangle. Now we know because it's a regular polygon, you can use the 1/2 SAN, 1/2 SAN, 1/2 AP. But if you know the side, like let's say the side's length is, let's just say 20 inches. Okay, that would mean all of these sides are 20, right? If it's equilateral. If this is equilateral, aren't all these 60? So if you happen to be given this information, instead of doing 1/2 SAN, you could just draw in the whole height. Forget about using just the apothem because the apothem only goes from here to here, and it is not half of the height, by the way. What would the height be? If the whole side's 20, wouldn't that make this 10? And if you draw in the height, you've bisected that angle, so that's 30. So that's the short leg. So that would make this long leg 10 square root of 3. So then, just like we did with the square, you don't have to use 1/2 SAN. You could just use the formula you know for a triangle, which would be 1/2 base times height. The base here would be 20, and then the height would be 10 square root of 3. So you could just multiply that out and get 100 square root of 3 without having to use the 1/2 SAN. That's only if you're given the side length. Think about that. I said a minute ago that the apothem is not half of the height. The apothem would go from right here down. That part's the apothem. What would this represent? That's a radius. So you actually could add the radius and the apothem together to get the height. I just wanted to point that out, that is not half of the apothem is not half of the height. Okay, so I just wanted to mention that there's another way to get that the area. And actually, there's a quick formula that's especially like maybe on the ACT that works for equilateral triangles. Instead of just 1/2 base times height, for an equilateral triangle, because it's a 30, 60, 90 triangle, it's going to work out that every time you take 1/2 the base, like if I call the base the side, the height is going to be, it's always going to be half of the base times the square root of 3. So half of the base times the square root of 3. So if you multiply 1/2 of the, I forgot the side there, the base is the side. So if you multiply that together, 1/2 times 1/2 is 1/4. S times S is S squared, and then square root of 3. So we can kind of put that together as S squared times the square root of 3 over 4. So that's a quick formula for finding the area of an equilateral triangle. Or sometimes you'll see it written square root of 3 over 4 times side squared. So that's, of course, the same thing. But I just wanted to throw that out there, or a quick way to find the area of an equilateral triangle if you know the side length. So it's the side squared times the square root of 3 over 4. Okay, so that's how you find the area of regular polygons. So now go practice. Talk to you soon.